So AG, let me go to the next page, becomes, well, I'm putting all the I components and J components together. So AG becomes R BG alpha BC sine 40 degrees sine 40 degrees minus R AB omega AB squared minus R BG omega BC squared cosine 40 I. Right? These are all the values that we know. There is no unknown there. Minus R BG alpha BC cosine 40 plus R BG omega, well, it's supposed to be omega BC squared sine 40 J. Now, whatever is here, we know RBG, well, is the distance from point A or point, let's say B, to point G, which is 300 millimeters. We know RAB, which is 700 millimeters. We need it for when we calculate AB. And we know all the angular velocities and angular accelerations. We are given all these values. So if you plug them in, from there, you'll get AG as, I have it here, minus 2, 947.9 I. Well, this is supposed to be 9 I minus 1690.6 J millimeter per second squared. So that's the acceleration of the center of gravity. Step 1 complete. Now let's draw a free body diagram, a kinetic diagram, and see what we have and put them there. So let me start with, I'm going to do that for link BC, right? Because I want to know what are the forces applied at point B. So I'll do this. I'll just draw a simple link, but this is BC. As simple as I could draw it, and point G is exactly in the center. I'm gonna copy this to use it for my kinetic diagram as well, and these two are the same. Exactly, they're not. Oh, apparently left have to be there. Okay, so this is point B. Now, what do I have? I have, well, as always, I have mass, right? Effect of gravity, mg, applied to center of gravity or center of mass, mg. I have reaction forces at point B. These are internal forces that exist between link BC and link AB. Since I'm drawing free body diagram for this link only, now I look at this forces, and there is also a couple, right? Because something is moving, right? I have to fix that. Something is creating this rotation, and that rotation is happening because of a couple applied to link BC at this joint. Usually in robotic arms, this is probably a stepper motor or any type of driver that is applying that torque or couple. From the right side, well, we have max and may, right, the component of acceleration. of center of mass. So MA GX, and this is MA GY, and assuming that the motion is happening this way, let's put also I G alpha there. Remove this G from there and put it somewhere is less confusing. This is point G. Now, let's write down the equations. Now, summation of forces in x direction would be MA GX. From there, well, BX is equal to MA GX. What is that? Well, I know what AGX is, right? This is this value. I already got it. M is 12 kilogram for this arm. So that would be BX is equal to minus 2,947.9 times 12, which gives me the value for BX. If you convert the units, since this is millimeter per second squared, and this is kilogram, you have to divide that by 1,000. That gives you 35 minus 35.375 Newton, which means BX direction is the opposite of what I draw there. In Y direction, summation of forces in Y direction is MA GY. That means BY minus MG is equal to MA GY. From there, you will get, let me see if I can, okay, BY, I can move that to the other side, M times G plus A GY. And then, well, I know what AGY is minus 1,690.6, right? And I know what is the mass, which is 12 kilograms. So 12 times, to be consistent, I'm going to convert that AGY to metric. Well, I'm going to convert that to meter per second squared. So divide that by 1,000, you will get minus 1.69, which gives you the value of BY, and that is 97.43 Newton. And this is BY. So these are the components of force, internal forces or reaction forces at point B. Now the final thing that I want to find out is what is that couple or torque applied there. So I'll write the equation for a moment, summation of the moments around point B. I'll take this direction positive. Some reason this time I took the opposite of the motion as positive. It really doesn't matter. You can take the other direction. That's what I usually do, but this is a little unusual, at least for me. So what we get is minus mg. Right? I have to multiply that by the distance it has from point B. I'm taking moments about B, and I use the first type of or first equation for a moment, first type, that basically uses mass moment of inertia around center of gravity and then acceleration of center of gravity, instead of finding the mass moment of inertia about the point that we are finding a moment about it. So that becomes, well, I know this distance is 300 millimeters, which means this becomes 300 cosine 40 degrees, and this angle is 40, right? This angle is, I don't want to make it so crowded here. So this is 40 degrees and this is 300. So this becomes 300, oops. This becomes 300, maybe I should have converted that. cosine 40 plus, well, I also have MB, whatever force I have applied at point B are gone. Taking a moment about point B, minus IG alpha minus let's see, mgx, right, the component of x, times the distance, which is 300 sine 40, 300 sine 40, and the component of y, so magy times 300 cosine 40. From there, I'm trying to find MB, or the couple applied, is minus IG alpha plus 0.3. Now I'm converting that 300 to meter. For some reason, I don't know why I did in the middle of the process. Cosine 40 times mg, that becomes then negative minus 0.3 sine 40 mg, and sorry, this is not mg, right? We got the component of mg. This is the component for agx. Agx is negative, and then we have the positive for component of y. MAGY. Pretty much this. The rest is just plugging in the numbers. I know everything. I know IG I'm given, it's 3. Alpha I'm given is 4. M is 12 kilogram. 9.8 for G, obviously, 12 kilogram. AGX, I have it there. Just remember to convert it to meter per second square. So it's going to be minus 2.947. And AGY, again, remember to convert it to meter per second square. Plug them all in, you will get the value for your M. So MB would be 17.212 Newton per meter. And that's the couple. So all 3 things that we were looking for, we found by just following those steps.